This is going to be super quick, so we will see if I succeed in my intent of making you all fall asleep in just 10 minutes. Of course, I'm kidding, but let's try to see if I can do that. Before we start, I need to introduce a bit. I work at Nearform. We are a professional services company, and we are deeply into open source contributions, as you might guess from my t-shirt right now, and we are mostly into Node.js development. We actually develop part of the core of Node.js and JavaScript standards and many other things. And we do a lot of architectural consulting. So this is where I'd like to go with my talk, given the experience into architecture review and consulting. But the idea for this talk started somewhere else. It started from an online course. In fact, every Monday evening, I have an online course with a dear friend of mine, which is called Gabriele. You can see him there. He's an excellent engineer, probably one of the best I've ever encountered in my career. He works in the RabbitMQ team and Kubernetes team, actually, in VMware. And we needed to find a way to explain what problem does distributed systems solve during this course. So junior developers, we had not very experienced developers, and distributed systems, it's such a complex topic for people who just entered, the programming world. So in order to do that, just following the previous talk, we decided to go with a CSV file, because it's the like the universal database format. Of course, I'm kidding again, but the idea was, please, students, create for us an API that uploads a large CSV file, like greater than 10 gigabytes, to a server, then read the file from the server, normalize the data, and store it into a database. That sounds pretty easy, right? But of course, this is not as trivial as it sounds. And this is also like a good interview question. So if you're willing to explore the interview questions, I find out you can determine if developer is experienced or not by answering this very simple question. So the vast majority of students, of course, came up with the following diagram. So basically, a user uploads something to an API server, the API server processes the data, and then inserts everything into a database. And so if we want to go into a more specific diagram, you see that we make a request, we do process the data as soon as we have them, and then upload the data to a database. Once we are finished, we send back like an OK message to the user. And of course, this leads to so many problems. Like this is synchronous, first of all. So if we have like thousands of concurrent requests, and that's the problem we tried to put after we saw the first diagrams. Well, once we start uploading and processing a few large files, we will run out of memory. So that's pretty easy, right? But a few more experienced students, still juniors, but a bit more experienced, came up with the following idea. So why don't we just put a load balancer and then distribute the load amongst different API servers, so we can create like new servers every time we need more, and so on and so forth. Of course, this is part of the solution, but does not solve the problem. I mean, if you have a very large amount of requests every second, this is not a plausible solution, of course. So this is where we found out that there is a way to explain how to solve these kind of problems with ice creams. So how many of you loves ice cream? Because I do. Awesome, this talk is for you. If you don't love ice cream, I will make you fall in love. Okay, so basically, let's imagine the following scenario like we were 5 years old guys. So we have an ice cream truck and we travel from city to city. It's really hot, it's summer, it's really hot, and people really want an ice cream. So people start to gather near to the ice cream truck. And as people came by, the more people we have, the more difficult it will be to serve all the people in a reasonable amount of time. This is a very common problem. So how do we currently, in real world, how do we currently deal with a large amount of people when there is a limited resource? With queues, of course, So we start creating queues, people start to organize themselves, usually, hopefully, but there is still a problem. There are people like behaving really badly. They try to cut the line. They want to be first. So we want to make sure that the first person in queue will be the first person to get served with their ice cream. So what we do, we typically hire a security guard. So this girl, in that case, will make sure that we will be creating a first in, first out queue. So the first person coming to the ice cream truck will be the first person to get served with their ice cream. So if we have a lot of people to serve, we will just scale horizontally. So we'll buy another ice cream truck, and then one other again. We are in a very lucky business. But when it comes to software architecture, things get a bit harder. We all know that. So we need to introduce a definition for distributed systems. Distributed system is a collection of independent computers that appears to its final users as one individual computer. So we put some barriers, to separate the queue from the ice cream trucks. And at this point, we don't care if we have like one ice cream truck, if we have 10,000 ice cream trucks. All that we care about at this moment is that we are able to serve ice cream fast enough and, of course, without causing very, very long queues. But to call a system as distributed, we need to specify 3 different rules. First rule is computers operate concurrently. So this is the case. We have ice cream truck number 1, which operates independently from ice cream truck number 2 or number 3. We have waiters and waitresses that are like the message broker in our architecture, that operates again independently. So a waiter can go to the ice cream truck with less queue to take the ice cream and bring it to the queue. That's just an example, but to the final user, let's say this girl here in the first queue, she doesn't really care if she gets the ice cream from truck number 1, number 2, or number 3. Most important thing to her is just to have her ice cream, So computers needs to fail independently, which means if ice cream truck number 1 gets on fire, hopefully it won't happen, but just in case, waiters are able to go to another ice cream truck, take the ice cream from there, bring the ice cream to the correct person in line, in a correct order, again, which is very, very important. And last rule we want to respect, computers do not share a global clock. So this is a bit more interesting and a bit more difficult to explain. By global clock, I actually mean like a wristwatch, for example. A watch, a device that can allow us to understand a given time. So let me give you an example. If we have like a unique source of truth, which is the golden watch, the pocket watch you see there, then we have like a smartwatch and a wristwatch, and we want to synchronize the 2 watches down here with the source of truth. Well, this is technically impossible to do to the limitations of the laws of physics we currently know. Let me go a bit deeper into that. So, to synchronize those watches, we have to make a synchronizing request. So we have to take watch number 1 and watch number 2, press like some buttons, and send a request. Then wait for a response. And of course, there is some latency. So even if we do that at the exact same time, there will always be some latency. In that case, might be the speed of light. So if I watch at my wristwatch right now to look at the hour, I need to wait for the light to be reflected to my eyes. And this is very, very fast, of course, but this is still a limitation for us because I will never be able to see with absolute precision the exact moment that I'm looking at my watch to coordinate with it. Of course, this is a huge problem in distributed systems. I fear I have no time to go deeper into that, but there are some standards to overcame these kind of issues. One is called NTP, which stands for Network Time Protocol, and one is called PTP, Precision Time Protocol. If you're interested in learning more about those protocols, there is an awesome article on geeks4geeks.org. They do explain that beautifully. So the solution required for our students was to satisfy the following rules, the rules we just saw. So first of all, is uploading a large CSV file to a server a good option? I mean, if we have one single server and we try to upload many different CSV files with large sizes, is that a good option? Is it a good option to block the entire server every time we want to upload something? Well, maybe we want to use an object storage, which is like let me simplify, a layer of abstraction over file systems. And it's more complicated than that, I know. Let me be shallow for a moment. Then we might use like or any kind of queuing systems or message broker, so that as soon as we deposit a file into a bucket, for example, we will be triggering a message so that a consumer, so a separate server, can take charge of consuming the new file, normalize the data, and upload something to the database. And again, we will store our data into the object storage, and as soon as the consumer will be over in processing the data, we'll be pulling some new object storage path, and we'll try to normalize and insert data again into the database. So this is the last part, of course, the database, and an API server. So an API server such that if we want to test that we actually have our data, we can do that without using a consumer, which is not meant for that. So the whole architecture schema, and this is very, very, very simplified again. We have a user. The user sends the CSV file directly to an object storage, gets triggered, RabbitMQ gets triggered, consumer says, oh wow, there is something new inside RabbitMQ, let me pull that. So we'll pull the path from the file, we'll download the file, normalize the data, insert everything inside a database, and then the user will be able to require data as soon as we put it into the database. So have we respected our rules? Do computers operate concurrently? Yeah. Do computers fail independently? Yes, in that case, of course, Rabbit, for example, could fail, but even though it's a super reliable software, we can use clusters so that if it's a distributed system on its own, so it takes care of those rules independently, okay? Do computers share a global clock? This is not needed in that example. This is something you might want to care about when you actually build distributed software such as RabbitMQ, as I was saying. So what problem did we solve in the end? We were able to move synchronous workflow to an asynchronous one, where if something fails, it won't attack the whole system. So the whole system will be up and running, even if an individual part will be failing. So that was very, very quick, and that was me. Let me present before I leave. I am Michele. I work as a senior software architect at Nearform. I'm a Google developer expert and a Microsoft MVP. I'm also the author of Lyra, the first full text search engine capable of running on edge networks such as AWS Lambda at Edge and Cloudflare. So if you're interested in that, I will be around, of course. And that was all for me. I will leave that a couple of seconds so you can reach out directly, mostly on Twitter. This is where I live most. And thank you again for this quickie.